lab, which is coming out a little bit different here. We are going to be talking about the actual construction of a database. I wanted to talk about, like, for instance, how the databases actually come together. Like, what should you be thinking as you're actually designing a database? Now, this is because when you put together a database, it's not just a matter of sitting down and writing code. I mean, you may have done that in other courses here, and maybe that got you by. But actually, though, when you write a database, when you actually put together or implement code for a database, we have discussed so many pieces that have to come together. For instance, the most important piece is the relationship between the data. But you're really in this slide that you see right here. Hopefully, you can maybe I can get some of the stuff off the screen here so you can see this. But in this slide right here, there is let's see full screen. I don't know if that helps. But in this slide right here, you're seeing that if you're designing some big structure, now the biggest structure I could think of was this baseball stadium here. Now, this stadium cannot just be put together in an afternoon, and it cannot just be put together by people coming together and putting seats and digging dirt and just doing simple things like that. Instead, in order to build a stadium, you have to spend some time designing it. And it's the same thing for your database. In order for you to build a database, you really have to spend some time thinking about how the pieces are going to come together, because this is how your system is going to, your system has to function in some way. I would say that when you're putting together the actual code for your system, the code is not going to be the difficult piece. In fact, the code is probably the easier piece for the whole database. I mean, we've already done this before, where we're putting together, code for building tables or creating queries or doing other things. And so that's not, the code doesn't change. It's usually the same old stuff. And when you first see it, it might be challenging, but after a while, it's just the same old code again. The challenge actually for building a database comes from the development, actually going to figure out how the pieces come together, how the design should be, and then how it's going to be used. And so I wanted to spend some time just to talk about that today, because we really haven't breached this topic here. We really haven't talked about how databases are actually put together here. And so I put together these kind of funny little slides here where we're using Jeff Bezos from Amazon. He's going to be the voice in our ear, who's going to be talking about how things come together. But he's really asking us, when we put together our database here, he is going to remind us that we have to consider what the purpose of this database is all about. Like, what is it supposed to do? So when you design something else, like if you design a car or something that's some kind of vehicle that moves people or machinery or parts or something over great distances, you have to think about what kinds of parts is it supposed to contain? Where is it supposed to go? What kind of terrain is it supposed to be used in? These are the same ideas about databases. What kind of data is going to go into the database? What kind of people are going to use it? Will it be used by people at all? Will it be used by machines? And so how is this database going to be applied? And so that takes you into the design of the system here. So the design of the system is figuring out, really, you haven't figured out the variables, and you may not have figured out all the relationships yet, but you know what it's supposed to do. And that is actually very, very important, because if you're just putting together a database where you have no real idea what it's supposed to do, we don't think about this, but it's going to fail, because when it starts taking on some kind of role where it has to do some important work, it's probably not going to do that role very well. And then you'll have to go back and reapply things and adapt pieces of code. And so then you're just kind of like going back to the design stages and reworking things. And so while that's all possible, and that does give you a database, it's not a terrific database. And so the database will be malformed for your company or your organization. And one of the troubles is that you do not want your organization held back by faulty software. In fact, you want your software to be supporting the organization wherever that organization is going. And so the design of the system here is actually a very big piece of your whole system. Now then, I'm seeing here, okay, so then the next part is about the construction, and the construction is about figuring out the relationships. First the relationships, and then the programming. And the relationships is about how the data is actually going to slot together. Now, as we've discussed this before, there's been a lot of discussion, or there's been a lot of data that goes into our databases, different types of data. And so because we have all this different types, all this different data, we really have to figure out how it's all going to be kind of tied together. And one of the most important things that I think we've mentioned, I mean, one of the most important pieces, I think you can find this in one of these slides here later on, is that every table in the database must be connected. And that connection really is the relationship. And so if you have a table in your database which has no relationship to anything else, then you cannot query that data. You cannot get to that data. And so the relationships are very important, and then you have to program those relationships. And then next you have the data entry, and then you do the information retrieval. The information, this is your query right here. But notice though that the queries is actually a very, very small part about the database operation or the database use. Most of your energy will go into this part right here, where you're looking at actually building the database and putting everything together. And so that's really where this class is taking us. We're trying to go through databases and look at these at SQLite databases, and we'll go into other kinds of databases. But we're looking at databases to work out how can we design them better. Now, the point of this whole course is that while today, in 2020, these databases that I've chosen for this course, in other words, SQLite, then we have Neo4j, we have Mongo, we have Cassandra, and there's some other ones in there too that we mentioned. While those databases are popular systems for today, they may change. And that means that tomorrow the databases might be something different. We may have some other system. And so the thing is, all of these databases function in the same way. And so if you know how to arrange your data in a way that there's a relationship between one piece of data and the next, then it shouldn't matter what database you're using. You should be able to play on that hardware or that software. You should be able to make use of any kind of technology here, because all databases serve the same kind of purpose, and that is to give you not all the data that you put in there, but give you the selected data that you want from a database or from their data. Anyway, I think that's everything else I'm going to say today is a subset of that I've just mentioned. So that's just your piece of, that's just your monologue. Now I wanted to kind of like go through a sample. This story that I'm about to tell you is partly inspired by my own internship with databases when I was working for a company, but also though I think that a lot of people who work in databases or database admins go through the same thing. So I wanted to talk about like the design of a database for a fabricated bookstore, which is called Fantastic Books. So typically what happens is that a bookstore manager or the owner will decide that it's time for a database. We need some system here where I can combine all information about my company. I want to know everything. I want to know about my customers. I want to know about the people who sell me books. I want to know about the people who are the authors who come in to sign books. I want to know about the employees who work for me. I want to know about the human resources aspects. I want to know about how long people have been working. I want to know everything, everything. And I want reports. And this is what clients will always say. They'll always say that I want reports. I want information everywhere. I want everything. But the thing is, though, that as Jeff Bezos puts it here in the salmon color, that is that the customers really know, or the clients really don't know what they want. They just know that they want information, but they don't really know what that information is going to look like when it comes to them. And so that is where, going back to the design stage here, you now have to figure out, well, what is it that this database is supposed to do? So going back to my slides here, the first piece is the analysis of usage. What is the purpose of this database? So now you have to figure out, like, well, what is it going to do? Why do you need all this information? I mean, are there pieces of information that perhaps you don't need as much as that? I mean, maybe you don't need everything. Maybe everything could be in the database, but you don't need it like all the time. Maybe. And so they do know, these customers though, these clients that you may have, they do know that they need something here. They want to have maybe some kind of on the left here we have a receipt from a purchase of books, and on the right, this is probably what you're going to be getting as a receipt when you buy books. Nothing is really written down, nothing's recorded. It's all just kind of written out by hand on pieces of paper. That's even a napkin I see, and so it's not like it's not a legal record. So they do know that they want some information. They want it written down. They want it archived, but they don't know anything about how to do this. And so this is where you have to kind of come together and figure out, like, what is this purpose? How is it supposed to function? How is it? You're starting from nothing here. And so you look at your information and you think, okay, well, let's look at the company and see what kinds of information what do they collect? What do they have? And you'll find that the information is, is about the books that they sell, the customers that they have, and so on. And so once you figure out what data is available, that might help you to figure out a potential purpose of this database. And by that I mean how that information could be used, what you could do with this information to assist the business. I mean, after all, that's why we create this database. It's to assist the the business, so that they have the information when they need it. When they need to know how many books they have on the shelves, of which type, of what in each section, they can find it. They can find that information. And so all these questions are all going to come together here as you're looking at this data, and then you're weaving them all together and figuring out how you can actually make use of this data to assist the business. And that means also, like, what reports does the company really need to have, or the organization really need to have in order to be assisted. So you're just kind of going, and this is actually a very frustrating job to do, because there's so much information that some companies have. But once you've figured out what that information is, once you have that information, then you start making your what's called the entities and attributes. Remember, an attribute is the column headers in your tables. So your tables you might put together. You might say, okay, well, I'm finding information about customers. I'm finding information about employees. I'm finding information about books and sales and purchases and wholesalers. And so if I have this information, then perhaps I could use this, I could put it into my database and use it perhaps to help my business grow. And so you put together your information in some way. Now, one thing is that you have to figure out, like, how you can, kind of tie this information together here, like the customer table, the employee table, the book, the sale, the purchase, wholesaler. These are all separate pieces of information that you have in your database, which must be brought together. You have to remember, your schema has to have a link between every single table. And so you're trying to figure out, like, how you can put everything together. But also, though, this word here, differentiate rows, remember what that's talking about. That's talking about finding maybe a primary key for each table to guarantee some level of uniqueness for every single row in the book, or in the table. I say book because imagine, for instance, that a bookstore has 10 copies of the same book. Does that mean that you'll have 10 entries for that book? Well, if you did, then that means that your table is going to just explode, and you'll have all this extra data in there, and that might slow things down a bit. And so you might want to figure out some kind of, some other system here where you have an ID that relates to a specific book, and then you have another column that talks about how many of that book is inside, how many of that book you actually have on the shelves. So then this is what you're going to do here. So you have this to find your unique rows here. We have used customer ID. We've created a customer ID, an employee ID, an ISBN, a sales ID, a purchase ID, and a wholesaler ID. These are to act as my primary keys, as we discussed last time, where every single row now has some accountability. That means you can locate each row because it has this unique code that separates this from another row that has, where the other data is seemingly all the same. So we create these codes ourselves, and this is actually something that you have to spend some time thinking about, because you want to create a customer ID system or an employee ID or something for which you have, like, many customers that you could add to this thing here. You don't want to have like a 3-digit. Your rule is that you have a 3-digit number, and that's it. That means you can only have up to 1,000 customers as your IDs here, as who you can give IDs to. And so you need to come up with a system here where, for instance, you can have as many customers as you like, and you're never worrying about redundancy. Anyway, this is like a combinatorics type problem. Then we need to link our tables together here. So this is about, by linking, what I mean by that is that we're finding some kind of relationship. So you can see that, for instance, the customer table, which is right here, and the sales table are linked. So for instance, they're linked. It's not a great link. We have the customer ID in the customer table, and then we have the customer ID in the sales table. And you might think, oh, that's great. Okay, fine. We have achieved some kind of link, and this is good. In the employee table, I see you might need to know, for instance, who works at the store, who sold you the book So for the sale, you might have an employee ID. And that's another piece of information that you would add to this table. But these are actually separate pieces of information here. So that means that if I update the customer ID in the customer table, or I update the employee ID in the employee table, then these pieces of information, as it stands, are not going to get updated in the sales table. Instead, I need to go to the sales table and actually manually update those two IDs. So this is, it's not a great system here. I do have links, but it's not a great system here because if I change the customer ID, if something happens and I realize that the customer ID has to change, then I have to go back and find all the cases of that customer ID in sales and also change those. And so that is going to take some time. So it's not a great system here. And so anyway, well, maybe it works for now here. Next, what we need to do is figure out the normalization here. So normalization is where you're kind of putting together, in fact, I have a slide here. But you're kind of putting together information like types of information into the same table. I'll just read this. It's the process of organizing data in a database. This includes creating tables and establishing relationships between them according to rules designed both to protect the data and to make the database more flexible by eliminating redundancy and inconsistent dependency. So the big thing is that going from here, where the database was not normalized, to perhaps here, where the database is normalized, or at least we're trying to normalize things, we're normalizing things a bit. Here is to kind of guarantee that the use of the database, as you're using the database does not become so filled up with redundant data, or the wrong data doesn't start showing up in each of these attributes in the wrong places here, so that the database is rendered useless. And that can happen. You can make a database and it's absolutely perfect and everything comes together nicely, but if you have no constraints to actually limit how people are supposed to use it, then it just doesn't work very well at all. In fact, if you start putting data in the wrong areas and the wrong attributes, then that just makes your queries come up short. I mean, you can't actually get any information that you're looking for because everything is mixed around. It looks like kind of one of my database teachers said, a badly formed database where the information is like scattered all over the place is like a scrambled egg. You can't put the parts back where they are. You can't separate the yolk from the whites. And so it's like this, you have this scrambled egg database. I think that we had this just after breakfast. It was a 9 a.m. class. And so I'm thinking that he was probably thinking about breakfast as he was teaching this class. And so I think he had scrambled eggs most days. Cool. Okay, so anyway, there's this. And so the normalization process is putting together these tables in a way that kind of makes sense. It's logical, and it allows people to use this database or to actually, to add information here without having to take a class in how that database comes together. It should be something normal. It's like something relatively kind of, I guess non-abstract. It should be this regular logical way of putting our data together here. So let's just look through this here. We have, for instance, in the customer table here, we have the customer ID, first, last name, address, so on and so forth. Then you have the employee information here. Now, the employee information is, you can see this, it's just about the people who work there. Now, you can say that, for instance, that these are both people, the customer and the employee are two different kinds of people who would be found on the floor of the bookstore. And so you might think, well, why not just make a big database that says people? Well, because that's not what normalization is all about. Normalization is saying, okay, I'm going to take all the people who are on the floor who are customers and put them over here, and all the people on the floor who are employees and put them over there. And so I'm basically creating these two separate tables here. Now, you could just have one giant table called bookstore people, and that's fine, but it's not really that's not really helpful to the. It's not going to be helpful to help you when you start looking for data in your database. It's not going to be. It's not a logical way of putting the information together. Everything just kind of gets mashed together, and it becomes hard to maintain. Now, you'll see that in each of these tables here, all the attributes that we have here really do concern they closely concern that table. Like the book, for instance, ISBN number, the title, the publisher, the publication date, the genre. All of these things here can only be about the book. They can't be about anything else. what I'm looking at here is the sales. You have the sale ID, and I'm thinking that by now these would be just simple foreign keys. You're not actually putting from the sale ID or for the customer ID here. Hopefully that's not actually putting information from the customer table into this sales table, but rather it is a foreign key, as we discussed in our last class on Monday. And so this customer ID is going to be a connection here between the sales table and the customer table. And then also you need the employee ID. And so for a sale to happen, first of all, you need a customer, and you need somebody who's going to be making the sale. So those are two different people that you would use. And so those are two different references to foreign keys in other tables that you'd have to have for your sales table. And so what I'm saying that you're normalizing your database, you're figuring out those links, those keys, all those relationships are all coming together so that the database is actually nicely put together without excess redundancy. Because remember, if you have redundancy, then your database becomes it's just too heavy to handle. I mean, when it's a small database, it's fine, but if you're trying to grow this company where you might hold information about customers for years and years, you may find that your database becomes so big that it just takes too long to query this database. In that case, you need to either rebuild the database, or you need to kind of remove some of the extraneous records that you don't use anymore. Do some house cleaning. So you don't want to have to worry about doing house cleaning in your data. You kind of want to hold on to this data forever, because as we'll talk about later on today, there's something here called data warehousing. And by data warehousing, you're creating a kind of a data or an informational historical record about your company. And you'd use that to find out how sales went during different years. You would never change this information, but you'd leave it the way it is, and then you'd go back to this thing and say, what happened in the year 1990 when I first opened this store? What kinds of books were selling back then? Are those trends coming back? If they are, how can I repeat some of the good business that I had? And so you could go back to that data and check it out, but it may be ancient data. I mean, 1990 was a long time ago. But still, it should be there. You should still be able to get to that information. Anyway, we'll talk about that. So that's normalization, finding kind of a logical relationship between all pieces of data, but reducing the redundancy and adding kind of maybe more logical, making the relationships more logically sound here by actually sticking things together that are supposed to belong. We have here something called inconsistent dependencies here, where I'll just read this here. Each of the fields in a table should have a dependency to a table. It belongs, like a piece of information belongs to this table, and it doesn't go anywhere else. And so if you have a table that talks about the name of the sales person at the bookstore, then that person's name should be in that table that talks about the names of the sales people. Their name should not be anywhere else. You wouldn't put that name in a bunch of different places around the database, because if you do, then that means that you have to update that name if you update that name. But also, though, it doesn't make sense. Why would you want to put that a salesperson's name in, like, say, the customer table, or say the book table? Or why would you actually put that information in? And so what you're saying is that you want to have the information actually that belongs in a table found in that table. So it shouldn't be like guesswork to find these things. So that's what they mean by these inconsistent dependencies, where a word or an attribute which doesn't belong on a table is found in that table, and that's just not, it's not logic. It's not logical to do that. Excuse me here. So let's see here. This is actually kind of an interesting thing here. If the representative's email, if you have a representative, that's usually somebody who comes from a company, who comes to a local business, and they try and sell that business certain things. So a representative from some publisher would come in and say, we have these books and those books and these books. Can we sell you a truckload of our books so that you can sell them in your store? That's the representative's job. And so you wouldn't put that person's name, that representative's name, into some other table that doesn't concern representatives here. You wouldn't put it in, for instance, in the customers table, because the customers table doesn't really concern people who are, the customers table concerns people who buy from the business, not who sell to the business. And so it's the wrong relationship. And so these inconsistent dependencies are where you're creating a rule for a table but some of the pieces of data that fit inside that table are not actually abiding by that rule. They're breaking the law. They're breaking the law here. Anyway, you'll see what I mean as the class goes on here. I think that'll make perfect sense. But remember, though, that every table has a certain kind of, every table is kind of like a nightclub here, where in order to be in the nightclub here, you have to get past the bouncers at the door. And if you can get past the bouncers, then you can get inside, you can dance and blah, blah, blah. All information is trying to get inside every single table, but each table should have kind of a set of rules which acts as the bouncers, and you can't let every piece of information into every table. Otherwise, you get those inconsistencies. And so hopefully that kind of makes some sense here. You want to make sure that every table has rules. If you're in there, then you have this, you behave this way. If you're data, and you're in this table, you behave this way, and so on and so forth. This is the entity relationship diagram. This is actually quite important. You'll notice that in this database, every table is connected. That means there should be some kind of link. Maybe in some cases there's 2 or 3 different links. As you can find, for instance, in the books table, the books table has links to 1, 2, 3, 4 different tables. So it's fairly well connected here. But you have other tables, like, for instance, the customer table, which has a link just to one table, which is on the left, which is linked up to the sales table. And while that's okay, it's not a, it just needs a connection. It doesn't have to be like heavily connected where it has like 5 different connections or 4 different connections as in the case of the book. But it does need to be connected in some way here. And so if you have a table here where you can put your finger on that table and you can't trace that table to another table, then that means that one of those tables is not connected. Every table must be connected in this network. Now, here's what you see when you're designing a database. This is part of the design. Going back to our early slides here, where we're actually talking about the design of the system here. This is the design. So when you put together this flow chart here, it's not a flow chart, this is actually called an entity relationship diagram. But when you put together this, you can see how the data flows. You can see how the data will move from how the queries would work. So for instance, if I wanted to find information about books, then I could go by way of the publisher. In other words, my query would be asking a question such as, what books has this publisher sold me this year? Or I can go by way of author, where I could say, which books do I have which were written by Conan Doyle? Or I can go by sales line, where I'm saying, how many Harry Potter books did I sell last quarter? Or, for instance, I'm looking at the purchase line table now, and that's connected to books. And I could say, how many books were bought from, some specific, some wholesale group, some company, by how many books did a representative sell us last year? It's like, so by looking at this kind of, this diagram, in your mind's eye, you should begin to kind of think of ways of getting the information out of the database. And by thinking of the ways of getting information out of the database, what that means is that you're able to start thinking of the code to write the query to actually harvest the information that you're looking for. So we have these relationships, and so all these relationships are actually fundamentally necessary. We're going to talk about how we can use these relationships across like broader tables here. For instance, if I wanted to connect the customer to the wholesaler, that's on the left side to the right side. You can see that the customer is connected to the sales ID. The sales ID is then connected to the sales line. The sales line is connected to the book. The book is connected to the purchase line. Purchase line is connected to purchase, and purchase is connected to wholesaler. So that's already a very complicated query, but the code makes it possible to get that information. And I'll tell you, in most cases, databases like this for companies, a person actually isn't running the query. We'll be talking about that later on. A person is actually not doing this query. Instead, the query is going to be run by another machine, a piece of software. And so it doesn't really matter how big the table could be. It doesn't. As long as a query can be written. So in other words, your software that you'll use to manage this database will worry about writing the query for you. You just have to worry that there is actually a path that gets from one table to another table. Oh, wait. So before I move on here, you'll notice that in these tables between author and book, I have many-to-many and a little arrow. I have a primary key. I have some red text up here. You can see that I'm adding some foreign keys and some primary keys. Those things we've already discussed. But what I'm actually putting here is this many-to-many. Now, many-to-many is on the next page here, where this is part of the code that you have to think about when you're writing or designing your database, because this will inform your queries. So we have these relationships which concern how much information do I have in one table, and how does that information relate to information in another table. So we call this like the one-to-many relationships, or the many-to-many relationships, or the one-to-one relationships. And if you think about it in terms of this, you'll see that every person here has fingers. I'll just assume that everyone does, that everyone has fingers. So every person has many fingers. And so one person has many fingers. But each finger belongs to one person. You don't have a finger that belongs to a multitude of people, because that's disgusting. It just doesn't happen. So we have this relationship here where you have to think about, as you're putting your database together, how does the data in one table relate to the data of another table? So here we have at the bottom here in figure 611, we have supplier and part. Now these little, and I wish I could point to the stuff that you can't see what I'm talking about here, but the two little scratch marks here next to the supplier, and the two little marks next to part, the marks on the left-hand side of part, those are markings that you use in this graphic. Those are markings how they use to describe the one-to-many relationships, or the one-to-one relationships. And I use the same relationship up here in the person and fingers example here, where you have these two ticks that are right next to on the person side. That means one. And where you have this basically a less than or equals, actually it's a less than sign here. That is for fingers. And so you're saying that there are more fingers per person than there are persons for fingers. And it's just a markings that they use to draw out the one-to-many relationships in these databases. Every single book that I've ever read on databases has a different system, I assure you, a different system to mark one-to-many or many-to-one. It's crazy how these authors can't just agree on some system of indicating that this table has a piece of information here which relates to many different cases in another table. I mean, it's a very simple idea. Anyway, but looking at this table, the relationship entity diagram, I'm looking at the graphic down here at the bottom. We have suppliers, so we have one supplier sells many different kinds of parts. So you can see the two ticks that are here for supplier, and you see the less than parts. So you can see there's more parts than there are suppliers in this relationship. So each supplier sells a multitude of parts. Now, many parts here, and let's read this. This is what this is saying here. It says that one part has many different line items. That is true. If you're writing up the receipt, for instance, your line item may be information about, how to use the parts, safety, maybe it's applications, it's other things. And then you have, for instance, each line item belongs to, there are many line items belonging to one order. And so one order has many different line items, but each line item doesn't have multiple orders. And so if you think in terms of the person and fingers idea, or maybe the supplier and parts ideas that you see here, that may help you to establish how your one-to-many, your many-to-one, one-to-many, how your relationships are going to unfold in your database. So I wanted to spend some time actually talking about this one-to-many, many-to-one relationships, where, for instance, on the left here for A, that's a one-to-one relationship. That means, and this is kind of like high school algebra here, when you're talking about functions, but each entity in the figure part A here, big A maps to big B, that's on the left here. So you can see that A1 maps to B1, A2 maps to B2, and so each entity in A actually maps to a specific entity in B. Now imagine for a second that these are not just blobs that contain squares, but actually big A and big B are tables. And so in big A, you have data, and in big B, you have data, And it seems that there's a one-to-one relationship between whatever the data is in big A with big B. And so maybe, for instance, you can say that it's getting back to the hands and fingers. Maybe, for instance, big A is fingers and big B is rings. Maybe each finger has one ring, each ring has one finger. And so it's a one-to-one relationship. Now, on the left-hand side of on the right-hand side of this figure, we have one-to-many, where we have big A, that set maps to big B, but you can see that A sub 1 on the right-hand side maps to B sub 1 and B sub 2. And so that's a one-to-many relationship. And you have to think about what those relationships are at the time of designing your database, because that's how you're going to be writing the code to maintain this database. You can see that A sub 2 relates to B sub 3 and B sub 4, but A sub 3 in this case, in big A, that relates to B sub 5. And so that's a one-to-one, but in general, the idea is that you have a one-to-many relationship. Going to the next thing here, you can have a many-to-one, which is very, very similar, where you have multiple things in big A pointing to this one thing in big B on the left. And on the right, you have many-to-many, where you may have, for instance, each thing in big A could map to multiple things in big B, and things in big B could map to multiple things in big A. So I'm talking about this because this is actually the logics that you need to consider when you're putting together the code for your tables. The many-to-one, one-to-many is actually a part of how your database is going to be used. And this will help you to kind of work out how the code should actually hold the data. This is maybe a more realistic example of the many-to-many relationship, or one-to-many. Our book, annoyingly, does not use the same markers that I just discussed earlier. Instead, our book uses big arrows. And so the first, at the very, very top of this diagram here, we see instructor and student tables here. This is a one-to-one. So this is saying that there's one instructor for every one student. It's a one-to-one relationship. So each student has one instructor, each instructor has one student. That means that your college class here you'd have to have, as many students as there are in the class here to teach the class. And so if you have a one-to-one, that means that every student, you basically have a tutor system here. So every student has one instructor, every instructor has one student. So that's the one-to-one. But actually, that's not how things work here. Instead, we have, I'm sitting here in a class. I see your colleagues are actually right next to you in this classroom here. There's people physically here. There's people online. And so then there's one of me. And so I am an instructor here, and I have many students. And so it's one of me and many students. So it's one to many. And so you're in part B in the middle of this. That is a one to many. That's usually how things work. You'll see that the bold arrow is on the instructor side, which means there's only one instructor. How they came up with that way of drawing this out, I will never know. But still, that's what this means. If you whatever the bold side is where there's only one of something. So here's the one to many. By the way, this diamond-shaped advisor piece in the middle, that's a piece of information to describe what the relationship is between instructor and students. So that's how you draw it out that there's this advising going on. Finally, we have many-to-many, and there's no heavy arrows here, but that means there's many instructors with many students and many students with many instructors. That's usually how things work in this college, where you have one instructor who has many students, and many students have many instructors. And so you have a many-to-many type of relationship. So when you have a many-to-many type of relationship, that's where you need to start thinking about keys, primary keys, foreign keys, those kinds of things, to be able to kind of map those two tables together in some system where you can actually keep track of exactly who is it that the instructor is teaching and who are the instructors of each student. And so you need those primary keys in place to ensure that you get that relationship. That is why we care about this many-to-many relationship. So this is another database that I found online here. This is a medical data by Open MRS. They cover every time a patient goes to a hospital. Information is collected on that patient, and so that information is ultimately poured into a database which they have that they control. And the database tables are like this. There's a bunch of things there, but you'll notice that each table, excuse me, each table is connected. There are no tables that are just floating in space that have no link to them. And you have to have that because that's how you connect that table to everything else. But as complicated as this is, remember what I said in that it's usually not a person who's writing code anymore to actually harvest the information. In other words, in this case, you probably have some piece of software that actually runs this database. We'll talk about that in a bit here. I mean, not today, but later on down the class, how to use an automated system to run your database, which is actually kind of fun. So here we have this one-to-many, many-to-one relationship where what we're doing is we are, again, this is a kind of the same, it's the same, the one-to-many, many-to-one markings that we see on each of these relationship lines is the same as as we saw here. In fact, I chose a graphic that I found that has the same markings, so everything's kind of consistent. But you can get an idea that the instructor of this course, there's one instructor on looking at the left-hand side here. The one instructor teaches a course, but this is suggesting to me, in looking at this thing here, I can see that there's one instructor and there are many different courses, which is true. I teach 2 different courses. In fact, I teach 3, and each semester those 3 courses change. So there's one of me, and there are 3 different courses to teach. And now there are many different students, and there are many different courses. I'm thinking that most of you probably have 4 or 5 courses that you're taking, and so that's, there are many students. If you're making a database between students and courses, there are many students and many courses. Each student may take 4 or 5 courses. Each course may have 30 students in them, and so you have this many-to-many relationship that you have to keep track of. That to me suggests foreign keys. Now, students and seats, that suggests a one-to-one mapping because you can only sit in one place at a time. And by this, seat, I think this is meaning that if you think about every person on campus here has a seat, that means they have a place on campus. It's not like a physical seat, but I think in this case, it could be a seat number. But I think what it means is that, like in medical school, for instance, there's like 140 seats for medical school every season, and so if you're trying to get into medical school, they say that they only have 144 seats, and so once those seats have been filled up, then you are no longer they stop them. They don't look for students anymore. And so in this, I'm thinking that we have, I think at this school, like maybe 2,000 seats for students. That means that's how many places we actually, that's how we count our resources to look after everybody. Something like that. So I think that's what that seat table is doing. Next we have the course and section. Each course may have multiple sections. Each section may have multiple courses. How does that work? Well, you may have a course in computer science which has 2 or 3 different sections where it's taught on Mondays, Wednesdays, and Fridays, and also that same course is taught on Tuesdays and Thursdays, and perhaps another section where it's taught on Friday afternoon. Who knows? But section numbers, if you look at all the courses across the campus here, you may find that there are certain section numbers which are the same. So section 00 might relate to this course, because this is the only course that's taught in databases here. But you may have, for instance, other courses where they also have section 00. And so if I did a search for all the classes which are coming from section 00, then I should get a bulk of courses here. Anyway, I think you get the idea. I wanted to just go in quickly. I think we have like 3 minutes left here. God, time flies in this course, just flies. The next thing I want to talk about is that when you're actually designing your tables, there is software that you can use. This is a screenshot that I've stolen from Access, Microsoft Access. It's not the most recent software, but it's the idea is still the same, where you can draw out your tables, you can put together your field name, and we know that to be called the attribute. There's the data type, and we know that to be where we put like varchar, or we put text, or blob, or int, or float, or numeric, any of those things. And then you have this thing which I think is actually quite handy, a description. That's like the metadata that you'd use to describe, like, what is that data supposed to be that you're establishing in that table. And so this is how you can design like very sophisticated big tables here using. I think this is an SQL like mainframe type language here. SQL and SQLite are the same language, but Lite is designed to be used with a single user, whereas SQL is designed to be used with many different people at the same time. And so if you're designing, like this is on Microsoft SQL, you would have this software that helps you to build this together, so you can actually help people work together online and make your database very sophisticated. So it's actually kind of it's a cool way of actually putting together a database. No more typing code if you don't like writing code. And then once you've finished doing that, you can go into Access here. And I'm not pushing Microsoft products here, but I think it's still a cool product. And then you can push this. You can push a button basically, and then you can see what your relationship diagram is going to look like. And you can see whether all the tables are connected. And if they're not connected, you can see that because there's this graphic here where you'll see a table which will just be floating in space. But I think actually, though, that Access and seemingly all the other softwares that you'd use to design databases, I think they're smart enough to kind of point out that the data or the table is disconnected. I have no reference to anything else. Why is this table done unconnected here? But having a graphic like this does help, because when you start coding this thing, then you need to kind of have an idea about how the tables are connected, whether it's one-to-many. Okay, what do my keys look like? How should I worry about my uniqueness? Do I worry about row uniqueness? Do I worry about not nulls? If you have something like this to look at, you get an idea about how it's all coming together. Now, you can see just barely, I'm looking at the sales table. You'll see that in the sales table, as the customer table connects to the sales table in this diagram, Access has it where there's a 1 right next to the customer, and there's an infinity sign right next to the sales sign on that link. So this is saying that there's one customer, many sales, one-to-many. That's how they draw it out. And so when you see these diagrams here, sometimes it takes some time, and of course for me, every time I see a diagram, it's a different way of telling me whether it's one-to-many or many-to-one. In other words, it's a different way of informing me how I'm supposed to use my keys. You have to spend some time looking at this and kind of getting an idea about what is the system, or what's the markings here. I think actually that 1 and infinity is a more logical system. Again, I give kudos to Microsoft for their product here. I think it's a more logical approach to showing whether it's one-to-many or many-to-one. But anyway, that's just me. That to me makes more sense than these cryptic chicken scratchings on these boxes. But still. One thing I'll just go through quickly, and is that basically when you're running your database, it's forms that are actually running, or that actually do the database. You don't actually see the code, and so you're putting together forms to kind of create these things. And so your forms actually are the database. It's part of the database. And so the database system here is seemingly everything connected to the database, but you don't actually see the code for the database. And this is important because if you're a big company like Amazon, you need to be able to figure out an easy way for all your employees to work with your database so that they can locate seemingly any book. I think that we're out of time. I think that maybe the last slides are really not that important here. We've already mentioned the warehouses, how they're different from databases. Warehouses is like an archived history of the data, whereas databases you can change. And I think that if one thing I'd ask you to do is as a thought experiment here, there's nothing to submit, but look through these names here and see whether you can find a way of somehow organizing these things. There are different ways of doing this, but this is the kind of problem, or the problem that you'll be dealing with when you're sitting down to work with databases, to make a database. You'll be looking at pieces of information like this, and you have to figure out some arrangement, like how do I put them together? Anyway, I'm 2 minutes over. I'm sorry about that, everybody. That is class. Stay well, and I'll see you in lab today.